Hi guys, in this video we are going to talk about conversion between mass of a substance and the amount of that substance using a concept known as molar mass. Recall in a previous lecture we introduced this concept of a mole, and we said that if you have 1 mole of objects, then that means you have 6.022 times 10 to the 23rd objects. We defined this number, known as Avogadro's number, to correspond to the number of atoms in 12 grams of the carbon-12 isotope. Okay, so now it turns out that the mass of all elements are in fact defined relative to C12. And so as a result, an element's molar mass, every single element's molar mass in units of grams per mole, is numerically equivalent to the element's mass in atomic mass units. So this is very convenient. We can go directly to that periodic table, for example for helium, look at that average atomic mass of helium, and conclude that the molar mass of helium is 4.003 grams of helium in 1 mole of helium. Okay, so this is our molar mass conversion factor. And similarly, for the average molar mass of carbon, taking into account all those naturally occurring isotopes, we get a molar mass of 12.011 grams of carbon if you have 1 mole of carbon. And so on and so forth for all the rest of the elements on that periodic table. Okay, so now what we're going to do is see how we can use this molar mass read off the periodic table to solve some simple problems. Okay, so the first problem we want to look at is an example involving pencil lead, and we'll assume pencil lead is just pure graphite, all carbon atoms, and we want to calculate the amount of carbon in units of moles contained in a 0.0265 gram sample of pencil lead. All right, so proceeding as we always do, we're going to start off by identifying what information we are given. Right? We are given a mass of pencil lead, right, entirely carbon, of 0.0625. Now our goal here is to determine the number of moles of carbon that are present. So our little outline for our problem consists of simply converting grams of carbon to moles of carbon. Now, the molar mass that we just introduced on the previous slide is going to be the conversion factor. It's going to provide the conversion factor necessary for converting grams to moles. So remember on the previous slide, we read off the periodic table what that mass is of a carbon atom, and we're going to take that average mass and use it to construct this conversion factor. The fact that the average atomic mass of carbon atom is 12.011 grams per mole, we are going to divide the mass, the given mass of pencil lead, by that molar mass of carbon so that the grams of carbon cancels out and we will be left with moles of carbon. So we're doing the math, we are going to arrive at a final answer of approximately 2.21 times 10 to the minus 2 moles of carbon. Okay, so here's an example of just a simple one-step conversion. Okay, but of course, we could run into problems that require multiple conversions. So in this next example, we are asked to determine how many copper atoms are in a copper penny with a mass of 3.10 grams. And we're going to make the assumption that that penny is composed of pure copper, so it was minted before 1982. We're going to start off, as always, by figuring out what we're given. We are told that we have 3.10 grams of copper in that penny. And our goal is to figure out how many number of copper atoms. So when we're making our problem-solving outline here, our problem-solving path is going to consist of changing those units of grams of copper first into moles of copper using that molar mass, and then use Avogadro's number to calculate the number of individual carbon atoms. So if we go ahead and plug in these values, all right, so then if we go ahead and set up the two conversion factors, starting off with our initial mass of copper. We're going to divide by that molar mass of copper from that periodic table to get grams of copper to cancel out. We will then be left with units of moles of copper. Then multiplying by Avogadro's number, we'll cancel out moles of copper, and we will be left with units of individual copper atoms. Plugging it all in the calculator, you should come up with a value of approximately 2.94 times 10 to the 22nd copper atoms. Okay, so now let's work through one final example, and this example is going to require a little bit more work. Going to synthesize a number of different topics. It will, of course, involve the use of the molar mass. So in this example, we are going to be given an aluminum sphere. And we're told that this sphere contains a total of 8.55 times 10 to the 22nd aluminum atoms. Given the fact that it's a perfect sphere, and given this number of atoms, we want to determine what is this sphere's radius in centimeters. To help us along on this path, we are told that the density of aluminum is 2.70 grams per centimeter cubed. Okay, so if you're confronted with a problem like this, it's very natural to have to read this a couple times, and honestly, you might feel stuck. So remember, before you start trying to jump in and even panic or even try and solve the problem, I want you to stop for a second and take that first step of simply writing down what those given quantities are. All right, so remember, we are told the number of aluminum atoms and the density of aluminum. Okay, so given those values, what we need to do in our second step is come up with a series of steps that will allow us to go from that given quantity, aluminum atoms, all the way over to volume. Okay, so now we know from using Avogadro's number and our practice using Avogadro's number that we can convert from the number of aluminum atoms into moles of aluminum. And as we're seeing this mini lecture, we can use the molar mass of aluminum to convert from moles of aluminum into grams of aluminum. And then, once we have the grams of aluminum, we can use the density, our other given quantity, to arrive at the volume. Okay? Then finally, once we have the volume, we're going to need to apply another equation, which many of you might remember from high school. The volume of a sphere is equal to 4/3 times pi times that radius cubed. Okay, so that's our little outline. Now what we want to do is go back and systematically apply each one of these steps, starting off with the number of aluminum atoms. So we divide by Avogadro's number to get to moles of aluminum. We multiply by that molar mass to get into grams of aluminum, and then we're going to divide by the density because we want grams of aluminum to cancel out, and we want to be in volume units. Now remember, at this step, we have an answer for the volume of this sphere. But remember, our final answer needs to be a radius. So we need to apply a last step. So rather than rounding off at this phase, I'm going to go ahead and keep all of my units, right, that come out of that calculator there, but I'm going to make this distinction to point out that we only actually have 3 significant figures here, and so we're going to have to use that to guide our final answer. Okay? But for right now, what we're going to do is take this volume and use our equation for the volume, solve for R, and then plug in this volume into our equation for the volume of a sphere, where we've rearranged it and solved for R, solved for that radius. Okay, then again, carrying over all those units without rounding, we can plug into that calculator 3 times this volume of the sphere divided by 4 pi, take the cubed root, and then round off our final answer to 3 sig figs, and we will arrive at a radius of this aluminum sphere of 0.697 centimeters.